Look up tonight and count the stars. Not all of them. That would take lifetimes. Just the ones you can see with the naked eye from wherever you are. On a clear night, far from city lights, that number is around 2,000 to 3,000. Maybe 4,000 or 5,000 if conditions are perfect and you know exactly where to look. The ancient Greeks catalogued roughly 1,000. Tycho Brahe, the most meticulous pre-telescope observer who ever lived, documented 777. Now consider that the Milky Way galaxy contains somewhere between 100 and 400 billion stars. The ones you can see tonight, every single one of them, the full spread of the night sky from horizon to horizon, represent approximately 0.0000001% of the stars in our galaxy alone. And our galaxy is one of roughly 2 trillion galaxies in the observable universe. This gap between what your eyes show you and what actually exists is not a rounding error. It is not a matter of degree. It is a fundamental statement about the nature of the universe that most people never fully reckon with. The universe is not mostly stars. It is not mostly light. It is not mostly anything you can see or detect or feel. The universe is almost entirely nothing. Not nothing in the philosophical sense, not nothing in the poetic sense of emptiness or void, nothing in the literal physical sense. Space so empty that if you were placed into it randomly, the nearest atom to your body would be, on average, several meters away. Space so vast that the distance between stars is not measured in miles or kilometers, but in the time it takes light to travel. And light moves at 299,792 kilometers per second. Space so dark that human eyes, the most sensitive light-detecting instruments our biology ever produced, would register complete, total, absolute blackness for distances so enormous that the word enormous loses its meaning. Tonight, we are going to try to actually reckon with this. Not just nod at the big numbers, not just quote the statistics and move on. We are going to follow the darkness honestly, through the solar system, through interstellar space, through the galaxy, through the large-scale structure of the universe, and try to understand what it means that existence looks the way it does. Because there is something specific and genuinely unsettling about following these numbers carefully. Something that takes the ordinary night sky, something you have seen hundreds of times, and makes it feel like something you have never actually looked at before. If you are here because the night is long and you need something to settle into, stay. This is one of those subjects where the more carefully you follow the evidence, the stranger the reality becomes. And the strangeness is real. It is not exaggerated for effect. It is what the data actually says about what surrounds us. Let us start close. Let us start with the space between Earth and the Moon, because this is the shortest cosmic distance relevant to human experience. And even here, the emptiness is more extreme than intuition suggests. The Moon is 384,400 kilometers away, on average. This number is well known, but its meaning is less well appreciated. If you were to take every human being who has ever lived, estimates range from 100 to 110 billion people over the course of human history, and stack them head to foot, you would not reach the Moon. You would cover roughly 170,000 kilometers. You would need to stack all of recorded human humanity twice to reach lunar distance. In that 384,400 kilometer gap between Earth and Moon, there is almost nothing. Some debris, meteoroids, dust, the occasional artificial satellite drifting in unusual orbits. But the density of material in cislunar space is so low that it registers effectively as vacuum by any engineering standard. Spacecraft traveling to the Moon do not need to worry about hitting anything. The space is that empty. Now extend this to the scale of the solar system. The distance from Earth to the Sun, 1 astronomical unit, the standard unit used in solar system measurements, is approximately 150 million kilometers. Already, this is a distance that challenges intuition. If you drove a car at 100 kilometers per hour without stopping, it would take you 171 years to reach the Sun. Light covers that distance in about 8 minutes and 20 seconds. Pluto, at its average distance from the Sun, is about 39 astronomical units, 39 times the Earth-Sun distance, or roughly 5.9 billion kilometers. Light takes about 5.5 hours to travel from the Sun to Pluto, but Pluto is not the edge of the solar system, not even close. The Oort cloud, the vast spherical shell of icy objects that surrounds the solar system and is the source of long-period comets, extends to a distance of somewhere between 50,000 and 200,000 astronomical units from the Sun. The inner edge begins around 2,000 to 5,000 astronomical units. The outer edge, at 200,000 astronomical units, is roughly 1 light-year from the Sun, 1/4 of the distance to the nearest star. Light takes between 7 months and 2.3 years to travel from the Sun to the outer Oort cloud. Voyager 1, the most distant human-made object, launched in 1977 and travelling at approximately 17 kilometers per second, will not reach the inner Oort cloud for another 300 years. It will take approximately 30,000 years to pass through the Oort cloud entirely. And through all of that space, through the 300 years of travel before reaching the inner Oort cloud, through the 30,000 years of passage through the cloud itself, the density of material is essentially zero. Occasionally, an icy body separated from the next by distances measured in astronomical units. The Oort cloud, despite containing possibly trillions of icy objects, is so vast that the average distance between objects within it is enormous. If you were placed randomly within the Oort cloud, you would see nothing. No sun visible to the naked eye, just another star, the brightest in the sky, but just a star. No other Oort cloud objects visible, just darkness in every direction, extending to the horizon of your vision and beyond. This is still within our solar system. Now let us cross the distance to the nearest star, to Proxima Centauri, our closest stellar neighbour at 4.24 light-years. 1 light-year is approximately 9.46 trillion kilometres. Proxima Centauri is about 40 trillion kilometres away. Voyager 1, if it were headed in the right direction, which it is not, would take approximately 73,000 years to cover this distance at its current speed. In that 40 trillion kilometre gap between the Sun and Proxima Centauri, what is there? Essentially nothing. A few rogue planetesimals drifting in deep space, some interstellar dust at densities so low that even laboratory vacuums on Earth are denser. The occasional hydrogen atom. Interstellar space contains on average about 1 atom per cubic centimetre in the plane of the galaxy, compared to the atmosphere you are breathing right now, which contains approximately 26 billion molecules per cubic centimetre. 1 atom per cubic centimetre versus 26 billion molecules per cubic centimetre. That ratio captures something important about what interstellar space actually is. If you were placed in the middle of the interstellar void between the Sun and Proxima Centauri, your experience of space would be this: complete darkness. Not darkness in the sense of a dark room or a dark night. Darkness in the sense of no photons reaching your eyes from any nearby source. The Sun would be visible. It would be the brightest star in the sky, magnitude approximately -16.5 if you were 2 light-years away. Brilliant enough to see, but a point source, not a disk. Every other star would be exactly what they appear from Earth, points of light separated by vast dark intervals. And that darkness between the stars, that black between the points, is almost incomprehensibly far. From your position 2 light-years from the Sun, the nearest star in any other direction would also be light-years away. You would be surrounded by light-year scale emptiness in every direction, completely alone, in a way that being on Earth never allows you to actually feel. Let us now talk about the structure of the Milky Way, about the galaxy we inhabit, and what its spatial reality means for the darkness of space at a larger scale. The Milky Way is a barred spiral galaxy. Its disk, the main flat structure containing most of the stars, is approximately 100,000 light-years in diameter and roughly 1,000 light-years thick in the spiral arms where our solar system resides. The central bulge is denser, stars packed more closely together near the galactic center. But even in the most densely populated regions of the Milky Way, the distances between stars are measured in light-years. Our solar system is located in the Orion Arm, a minor spiral arm of the Milky Way, about 26,000 light-years from the galactic center. The stars in our neighborhood are separated by distances averaging somewhere between 4 and 8 light-years. The stars appear packed together when you look at the Milky Way band across the night sky, but this is entirely a projection effect. Thousands of stars at various distances along a line of sight, summing to produce the appearance of density. In three-dimensional reality, even the densest appearing regions of the Milky Way are almost entirely empty. How empty? Consider this. If you could shrink the entire Milky Way galaxy to the scale of the continental United States, roughly 4,500 kilometers across, the average star in this scaled-down galaxy would be approximately the size of a grain of sand. And the average distance between stars in this scaled representation would be approximately 50 kilometers. Grains of sand 50 kilometers apart, everywhere, in every direction. No matter where you put yourself in this scaled model, the nearest star would be 50 kilometers away, the next one 50 kilometers in another direction, and the space between them, representing the actual interstellar medium, would contain effectively nothing you could see or feel or interact with. Now scale back up to reality. Take those grains of sand and expand them back to actual stellar dimensions. The Sun is 1.4 million kilometers in diameter, and expand the 50-kilometer gaps back to actual light-year distances. Everything you see when you look at the night sky exists within this framework. The band of the Milky Way is this: sand grains separated by light-year voids, so many of them stacked along your line of sight that they sum to a visible glow. But the glow is deceptive. The glow tells you nothing about the darkness between the sources, and the darkness between the sources is, in volumetric terms, essentially everything. Поговорим теперь о конкретном числе, которое делает реальность темноты пространства особенно поразительной, о так называемом парадоксе Ольберса и о том, что его решение говорит нам о природе наблюдаемой Вселенной. The paradox was posed by the German astronomer Heinrich Wilhelm Olbers in 1823, though it had been discussed by earlier thinkers. The question is deceptively simple. If the universe is infinite and uniformly filled with stars, why is the night sky dark? Think about it carefully. If you look in any direction, your line of sight should eventually hit a star. An infinite universe uniformly filled with stars would mean that every line of sight, extended far enough, terminates at a stellar surface. And if every direction you look has a star at the end of it, the night sky should be as bright as the surface of the Sun, blazing white light in every direction, day and night, continuously. But the night sky is dark. The classical resolution offered in the 19th century, that starlight is absorbed by intervening dust and gas, does not actually work. The absorbed material would heat up until it radiated as much energy as it absorbed, eventually reaching the same temperature as the stellar surfaces and emitting just as much light. The darkness cannot be explained by absorption. The correct resolution, developed in the 20th century through the discoveries of the expanding universe and the finite age of the observable universe, is this: the universe is not infinite in time, even if it may be infinite in space. The observable universe had a beginning approximately 13.8 billion years ago. Light travels at a finite speed. Therefore, there is a maximum distance from which light has had time to reach us, a cosmic horizon beyond which the universe is not yet visible to us, regardless of what exists there. The night sky is dark because the universe is not old enough and not large enough in its observable extent for every line of sight to terminate at a stellar surface. Most lines of sight extend past the last star and into the cosmic microwave background, the afterglow of the Big Bang, redshifted to microwave frequencies invisible to human eyes, and beyond that into regions from which light has not yet arrived. The darkness is the signature of finite cosmic time. The black between the stars is the universe telling you that it has not existed forever, that there are distances beyond which nothing has reached us yet, that time itself has a beginning. This is what you are looking at when you see a dark night sky, not just empty space, the finite age of the universe made visible. Let us now talk about something more specific and more viscerally unsettling, about what it would actually mean to be in deep space, and why the darkness of space is not just a visual phenomenon, but a physical one with real consequences. Space is not merely dark, it is cold in a specific and extreme way, not cold in the sense of winter or Arctic temperatures, but cold in the sense of approaching absolute zero, the theoretical minimum temperature where all molecular motion ceases. The temperature of empty space, the cosmic background temperature in regions far from any star, is approximately 2.7 Kelvin. This is minus 270.45 degrees Celsius. For reference, the coldest naturally occurring temperature ever recorded on Earth's surface is approximately minus 89 degrees Celsius. The coldest temperature achieved in laboratory conditions is a tiny fraction of a Kelvin above absolute zero. The temperature of deep space at 2.7 Kelvin is almost at the theoretical floor of thermodynamics. This temperature, the cosmic microwave background temperature, is the afterglow of the Big Bang, the thermal radiation filling all of space at the temperature to which the early universe has cooled over 13.8 billion years of expansion. It represents the baseline thermal environment of the universe, the temperature that would prevail everywhere in the universe in the absence of local heat sources like stars. In this environment, a human body unprotected in deep space would not simply freeze, it would radiate its own heat into the surrounding void faster than any source could replenish it, cooling toward ambient temperature over a period of hours. The mechanism is radiation. All objects above absolute zero emit thermal radiation, and in deep space there is nothing to radiate heat back. The body's temperature would drop continuously until it reached the ambient temperature of space. But by that point, other things would have happened first. At the instant of exposure to space, the atmospheric pressure drops to essentially zero. The dissolved gases in blood and body fluids begin to come out of solution, nitrogen and oxygen forming bubbles in the bloodstream and tissues. The water in body tissues begins to evaporate, not boiling, but sublimating directly from liquid to vapor, because the pressure is too low for liquid water to exist. The lungs, if air is still held in them, experience barotrauma from the pressure differential. The eyes dry. Saliva on the tongue begins to boil. All of this happens rapidly. Consciousness is lost within about 15 seconds due to oxygen deprivation. The blood can no longer carry oxygen at ambient pressure. Death follows within minutes. The reason I describe this is not for horror, but for calibration. The darkness of space is accompanied by a physical environment so hostile to the chemistry of life that there is essentially no margin for error. The human body, which evolved to function within a narrow band of atmospheric pressure, temperature, radiation, and chemical composition, is completely unsuited to the baseline conditions of the universe it inhabits. We exist within a thin, protected envelope, the surface of a planet with an atmosphere and a magnetic field and a nearby star, and that envelope is vanishingly small compared to the volume of space in which it floats. The darkness is not just the absence of light, it is the environment, the temperature, the pressure, the radiation, the silence. All of these together constitute what space actually is, in contrast to the conditions that make life possible. Let us now talk about the darkness of space beyond the galaxy, about the intergalactic void, and what it means to be in the space between galaxies. The Milky Way is a member of a group of galaxies called the Local Group. This group contains approximately 80 known members, mostly dwarf galaxies orbiting the Milky Way and the Andromeda Galaxy, which are the two dominant members. The Local Group extends over a volume roughly 10 million light-years in diameter. Beyond the Local Group, the nearest large galaxy cluster is the Virgo cluster, approximately 65 million light-years away. The Virgo cluster contains over 1,300 member galaxies, possibly as many as 2,000. It is part of the Virgo supercluster, which also contains the Local Group, and the Virgo supercluster is itself part of a larger structure called Laniakea, a supercluster of galaxies roughly 520 million light-years in diameter, containing the equivalent mass of 100 million billion suns, distributed among approximately 100,000 galaxies. These numbers, millions and billions of light-years, tend to wash over the mind without leaving any useful impression. Let us try to make them concrete. The space between the Milky Way and the Andromeda Galaxy, our nearest large neighbour, at 2.537 million light-years, contains effectively nothing. The Local Group is embedded in what cosmologists call the local void, a region of space with significantly below-average density of matter. The local void extends for tens of millions of light-years in several directions from our location. But the local void is nothing compared to the great cosmic voids that make up the large-scale structure of the universe. At the largest scales, the universe has a specific structure. Matter, galaxies, galaxy clusters, superclusters, is arranged in thin sheets and filaments surrounding vast, nearly empty regions called voids. This structure, which cosmologists call the cosmic web, gives the universe the appearance at large scales of a sponge or a foam, dense structures on the surfaces of huge bubbles, with the interiors of the bubbles being almost completely empty. The Boötes void, a particularly well-studied example discovered in 1981, is approximately 250 to 330 million light-years in diameter. Its interior contains almost no galaxies. For reference, the entire Milky Way galaxy is about 100,000 light-years in diameter. The Boötes void is approximately 3,000 Milky Way diameters across. Traveling at the speed of light at 299,792 kilometers per second, it would take between 250 and 330 million years to cross it. In that entire volume, there are essentially no galaxies, no stars, no planets, nothing. The temperature is 2.7 Kelvin. The density of matter is significantly below even the already extraordinary emptiness of intergalactic space. If our galaxy were located in the center of the Boötes void, the night sky would look different from how it looks now. There would still be stars, the Milky Way itself, all the stars of our galaxy, visible in the sky. But the faint patches and smudges that represent other galaxies in our night sky, Andromeda visible to the naked eye as a smear of light, the Magellanic Clouds in the southern sky, dozens of galaxies accessible through modest telescopes, all of those would be gone. Instead of seeing the Virgo cluster 65 million light-years away, we would see the nearest galaxies perhaps 150 million light-years distant. The universe beyond our own galaxy would be a deep, featureless, empty black, darker than what we already have, darker than the already extraordinarily dark sky we live under. Let us now talk about something that took a specific measurement to discover, and that changes the darkness question in a way that is still being absorbed by cosmologists, about the cosmological horizon and what it implies about the darkness beyond what we can see. The observable universe, the region from which light has had time to reach us since the Big Bang, is a sphere with a radius of approximately 46 billion light-years. This number is larger than the 13.8 billion light-years you might expect from the age of the universe, because space itself has been expanding during the time the light was travelling, stretching the distances to sources beyond where they were when the light left them. Beyond the observable horizon, beyond that 46 billion light-year radius, the universe continues. Current cosmological evidence strongly suggests that the universe is very large, or possibly infinite, extending far beyond what we can observe. Regions beyond the horizon exist, contain matter, contain stars and galaxies, but the light from those regions has not had time to reach us. It is on its way, travelling at the speed of light, and it will arrive in the future. Or rather, the light from regions only slightly beyond the current horizon will arrive in the future. Regions sufficiently far beyond the horizon are receding from us faster than the speed of light due to cosmic expansion, and will never send light that reaches us. This means that the universe contains regions that are permanently inaccessible to observation, not because of any instrumental limitation, not because of any technical problem we might solve with better telescopes, but because the geometry of space-time combined with the accelerating expansion of the universe creates a cosmic event horizon beyond which signals can never reach us, regardless of how long we wait. The darkness beyond the observable horizon is different in character from the darkness between stars or between galaxies. The darkness between stars is absence of nearby sources. The darkness beyond the cosmic horizon is causal disconnection, regions that are not merely far away, but fundamentally outside our light cone, separated from us by a geometry that makes information exchange impossible in principle. There may be galaxies beyond our horizon exactly like ours. There may be planets. There may be other forms of life looking out into their own observable universe. We cannot know. The light from those regions, if it exists, will never reach us. The universe is not just dark in the places we can see. It is bounded by darkness we can never penetrate, regardless of the technology we develop, the telescopes we build, the time we wait. Let us now talk about what the darkness of space means in the context of the search for other civilizations, about what the size and emptiness of space implies for contact between any two civilizations that might exist in the galaxy. The Milky Way is approximately 100,000 light-years in diameter. If a civilization on the opposite side of the galaxy sent a radio signal toward Earth today, that signal would not arrive for approximately 100,000 years. If we responded, our response would not arrive for another 100,000 years. A complete exchange of two messages would take 200,000 years. This is not a technical limitation. It is not a problem that faster communication technology can solve, because faster-than-light communication violates the fundamental physics of special relativity. The speed of light is the absolute maximum speed at which information can travel through space. The darkness of space, the enormous distances between stars, imposes a hard limit on how quickly any signal can cross those distances. If we wanted physical contact rather than radio communication, if we wanted to actually travel to another star, the minimum travel time at any speed achievable by any technology we can currently conceive is thousands of years for the nearest stars. For crossing the galaxy, the timescale is millions of years, even at velocities approaching the speed of light. The silence of the night sky, the fact that we have not detected any signals from other civilizations despite decades of searching, is sometimes cited as evidence that we are alone. But the darkness of space provides an alternative explanation. Even if the galaxy were teeming with civilizations, the distances between them might be so large that their signals, spreading at the speed of light, have simply not had time to reach us yet. A civilization 10,000 light years away that began broadcasting 9,999 years ago has sent signals that are still 1 light year short of arriving. The darkness is not just visually dark, it is temporally dark. Even the information about what exists in the distant galaxy is travelling toward us at the speed of light, which means we are always looking at the past, always receiving information that is thousands or millions or billions of years old. The stars you see tonight are not where they appear to be. They are where they were when the light left them. Some of them may no longer exist. The light from their deaths may already be travelling toward us, decades or centuries away from arrival. The night sky is not a window to the present. It is an archive of the past, reaching back billions of years. Let us now talk about something specific about the darkness of space that is counterintuitive and rarely discussed, about the fact that even in the darkest possible location in deep space, you are not actually in complete darkness, and what this tells us about the universe. The cosmic microwave background, the thermal afterglow of the Big Bang, fills all of space uniformly. It is not visible to human eyes because it exists at microwave frequencies far below the visible spectrum, but it is everywhere. It is the photons left over from the early universe when matter and radiation decoupled about 380,000 years after the Big Bang, now cooled to 2.7 Kelvin through cosmic expansion. If your eyes could detect microwave radiation, you would see the universe glowing uniformly in every direction. A faint, uniform, nearly featureless glow filling the entire sky. This is the universe's minimum background illumination, present even in the deepest voids, even in the most remote locations imaginable. Beyond the microwave background, there is also the cosmic infrared background, the accumulated infrared light from all the stars and galaxies that have ever existed. Too diffuse and too redshifted to see with normal instruments, but detectable with sensitive space telescopes. There is the cosmic optical background, the integrated light from all galaxies. There is the cosmic X-ray background and the cosmic gamma-ray background from energetic events throughout cosmic history. The universe has accumulated a diffuse glow from 13.8 billion years of stellar activity, and this glow permeates all of space. You cannot escape it. There is no location in the universe so remote that you are outside this background radiation. The deepest darkness achievable is still bathed in the photons of cosmic history. This is the paradox of cosmic darkness. The universe is almost entirely dark. Dark in the sense that sources of light are separated by unimaginable distances. Dark in the sense that the overwhelming majority of its volume is far from any star. Dark in the sense that a human standing in interstellar or intergalactic space would perceive complete blackness. And yet the universe contains more photons per cubic centimetre of space than any other kind of particle. The photons of the cosmic microwave background alone, at approximately 410 photons per cubic centimetre everywhere in space, outnumber the atoms of all visible matter in the universe by approximately 1 billion to 1. Space is full of photons. None of them are at wavelengths our eyes can detect. The darkness is our darkness. The universe itself is saturated with the light of its own history. Let us now talk about something that requires holding two contradictory seeming facts in mind simultaneously, about dark matter and what it means that most of the matter in the universe is invisible. Everything we have discussed so far, every star, every galaxy, every dust cloud, every atom in interstellar space, constitutes what cosmologists call ordinary or baryonic matter. It is the matter made of protons and neutrons and electrons, the matter that can emit and absorb light, the matter that all of chemistry and biology and geology is built from. Ordinary matter makes up approximately 5% of the total energy content of the universe. The remaining 95% consists of dark matter, approximately 27%, and dark energy, approximately 68%. Neither dark matter nor dark energy interacts with light in any known way. Both are invisible by definition. Neither has been directly detected in a laboratory. Both are inferred from their gravitational effects on the visible matter we can observe. Dark matter, whatever it is, does not emit light, does not absorb light, does not reflect light. It passes through ordinary matter without interaction. It passes through you right now, tens of thousands of particles per second, without any detectable effect. It fills the space between and around galaxies in vast halos extending far beyond the visible stellar disk. The Milky Way's dark matter halo extends several 100,000 light-years from the galactic center, far larger than the 100,000 light-year visible disk. This means that the darkness of space is not simply empty. It is filled with matter that is dark not in the ordinary sense of unlit, but in the fundamental sense of not interacting with electromagnetic radiation at all. The dark matter content of the universe is 5 times greater than the ordinary matter content, and it exists everywhere, in the voids between galaxies, in the halos around galaxies, in the regions between stars, entirely invisible, entirely undetectable by any optical or radio or X-ray telescope. The universe is not 95% empty. It is 95% something we cannot see, something whose nature we do not fully understand, something that makes its presence known only through its gravitational influence on the 5% that is visible. The darkness has depth that our instruments cannot probe. Let us now talk about something that brings the cosmic darkness back to the human scale, about the specific experience of the darkest places on Earth, and what they reveal about our intuitions regarding darkness. The darkest skies accessible on Earth are found in a small number of locations: remote deserts, high mountain plateaus, isolated islands far from any city or artificial light source. The Atacama Desert in Chile, the Namib Desert in Namibia, the high plateaus of Tibet, certain locations in the American Southwest. In these places, on moonless nights with good atmospheric transparency, the sky is as dark as it gets on the surface of our planet. In such locations, the naked eye, under fully dark adapted conditions, can detect stars down to approximately magnitude 6.5 to 7. This reveals stars visible from nowhere else, nebulae visible as faint patches, the zodiacal light, a faint cone of light along the ecliptic caused by sunlight scattered off interplanetary dust, and potentially the Gegenschein, a faint glow on the opposite point of the sky from the sun caused by the same dust scattering light back toward us. The Milky Way in such conditions is not a faint smear, but a complex structure. The central bulge clearly brighter than the arms, dark dust lanes threading through the brighter regions, star clouds and star clusters visible as specific features rather than general glow. It is spectacular in a way that no photograph quite captures, because the eye adapts dynamically to the brightness variations in a way that a camera with a fixed exposure cannot. And yet even this, even the darkest sky achievable on Earth, is contaminated by airglow. The upper atmosphere glows faintly due to chemical reactions between molecules excited by solar radiation. This airglow sets a minimum brightness for the terrestrial night sky of about magnitude 22 per square arcsecond, a level of brightness that makes the sky measurably brighter than the true darkness of space, even in the complete absence of artificial light and moonlight. The truly dark sky, the darkness of interstellar or intergalactic space, cannot be experienced on Earth. Our atmosphere imposes a minimum brightness. The only humans who have experienced anything approaching the darkness of open space were the Apollo astronauts who travelled to the Moon, where the absence of atmosphere means no air glow, no atmospheric scattering, no extinction of starlight. Astronauts who shielded their eyes from both the sun and the illuminated Moon reported seeing a sky with several times more visible stars than from Earth, and with a quality of darkness that none of them could describe. But even in orbit, even on the Moon, the sun is nearby. The illuminated surfaces of the Earth or Moon are visible. The solar wind is present. The true experience of deep interstellar darkness is not accessible to any human who has ever lived. Let us now talk about what the darkness means for the scale of the universe's history, about cosmic time and how the darkness has changed over the life of the universe. The universe was not always dark. In the first few 100,000 years after the Big Bang, the universe was so hot and dense that matter and radiation were coupled. Photons could not travel freely because they were constantly interacting with charged particles. The universe was opaque, filled with a plasma so bright that its equivalent temperature was thousands of degrees Celsius. You could not see through it. Then, approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons to combine with protons to form neutral hydrogen atoms. This transition, called recombination, suddenly made the universe transparent. Photons that had been trapped in the plasma could now travel freely. The universe's opacity dropped to essentially zero. Light could travel. But there was nothing interesting to see. The first stars had not yet formed. The universe was filled with neutral hydrogen and helium gas, extremely uniform, with only tiny density fluctuations that would eventually grow into the cosmic web structure we see today. The photons released at recombination are what we now detect as the cosmic microwave background. Then came what cosmologists call the Dark Ages, a period lasting from approximately 380,000 years after the Big Bang to somewhere between 150 million and 800 million years after the Big Bang, during which no stars existed. The universe was transparent but utterly dark. No sources of light, no stars, no galaxies. Nothing but cooling gas in an expanding universe, extremely slowly contracting under gravity into the first structures that would eventually host the first stars. The first stars, called Population 3 stars, a category we have never directly observed because they no longer exist, are estimated to have formed somewhere around 100 to 200 million years after the Big Bang. They were likely very different from modern stars, much more massive, much hotter, burning their fuel rapidly and ending in spectacular supernovae after only a few million years. They produced the first heavy elements in the universe. Everything heavier than hydrogen and helium was forged in the cores of these first stars and scattered into space by their deaths. As these first stars ignited, their ultraviolet radiation began ionizing the surrounding hydrogen gas, stripping electrons from atoms, creating the conditions necessary for light to propagate differently through the intergalactic medium. This process, called cosmic reionization, transformed the universe from a neutral, gas-filled dark space into the ionized plasma intergalactic medium that exists today. The universe has been illuminated by stars, by quasars, by galaxies, for approximately 13.5 of its 13.8 billion years. But it was dark for those first few 100 million years, and before recombination it was not dark but opaque, and what lay on the other side of that opacity, at the very beginning, is still an active area of research. Let us now talk about something deeply specific and genuinely strange. About the discovery made in 1998 that the expansion of the universe is accelerating, and what this means for the long-term darkness of the cosmos. In 1998, two independent teams of astronomers, the High-Z Supernova Search Team and the Supernova Cosmology Project, published results showing that distant Type 1a supernovae were dimmer than expected. Type 1a supernovae are useful astronomical measuring tools because they all explode with approximately the same intrinsic brightness, allowing astronomers to use them as standard candles to measure cosmic distances. The dimmer than expected brightness of the distant supernovae indicated that they were farther away than the models predicted, which meant the universe had been expanding faster in the past than it is today, but not in the way that simple deceleration would suggest. Instead, something was causing the expansion to accelerate. That something is dark energy, the name given to whatever is driving the acceleration. Its nature remains unknown. It could be the energy density of empty space itself, the cosmological constant that Einstein introduced and then removed from his equations. It could be a dynamic field that varies over time. It could be something else entirely. We know its effect, the accelerated expansion of space, but not its fundamental nature. The implications of accelerating expansion for the future darkness of the universe are profound and disturbing. As space expands, galaxies beyond a certain distance from us are receding from us faster than the speed of light. Not because the galaxies themselves are moving faster than light through space, but because the space between us and them is expanding so rapidly that the light they emit cannot make headway against the expansion quickly enough to ever reach us. These galaxies are beyond our cosmic event horizon. We will never see them, and they will never see us. As the expansion accelerates over time, this event horizon shrinks in terms of the range of galaxies accessible to us. Galaxies that are currently observable, still within range for their light to reach us, will eventually recede beyond the event horizon as the accelerating expansion carries them out of our accessible universe. Their light, currently on its way to us, will be the last we ever receive from them. After that, they will be gone from our observable universe permanently. This process, the gradual disappearance of galaxy after galaxy beyond our observable horizon, will unfold over billions of years. In the very distant future, astronomers in our galaxy, if any exist, will see a progressively emptier universe as all the external galaxies recede beyond the horizon. First, the most distant galaxy clusters will disappear, then progressively closer ones. Eventually, even the Virgo cluster, currently 65 million light-years away, will recede beyond the horizon. In the very long term, the only galaxies remaining within our observable universe will be the local group, the roughly 80 galaxies gravitationally bound together, including the Milky Way and Andromeda. All of these will eventually merge over tens of billions of years into a single giant elliptical galaxy. The descendants of the Milky Way and all its neighbours will form a single merged system. Beyond that merged system, in all directions, the universe will appear completely empty. Not empty because there is nothing there. There will still be billions of galaxies just as there are today, but empty because they will have receded beyond the horizon, out of causal contact, invisible and inaccessible forever. The universe is getting darker over time, not because stars are going out, they will continue to be born for trillions of years, but because the geometry of expanding space is progressively placing more of the universe beyond the reach of light. The future is darker than the present, and the very far future, after all stars have exhausted their fuel, after the last white dwarf has cooled, after all black holes have evaporated through Hawking radiation over timescales of 10 to the power of 67 to 10 to the power of 100 years, will be dark in a way that the current universe is not. Not the conditional darkness of light that has not yet arrived, but the permanent darkness of a universe that has exhausted its sources of light and heat and settled into the maximum entropy equilibrium that physicists call heat death. The darkness of space is not a static condition, it is a trajectory. The universe began in a state where even its darkness was a specific kind of brightness, the opaque plasma of the early cosmos. It moved through a dark age. It was illuminated by the first stars. It reached a peak of stellar activity approximately 10 billion years ago, when the rate of new star formation was several times higher than today. It has been declining since then, producing fewer new stars each billion years, its overall brightness gradually decreasing as old stars die faster than new ones are born. We live in a universe in decline, still brilliantly lit by cosmic standards, still producing hundreds of new stars every year in the Milky Way alone, but less lit than it was and trending toward a darkness that will, in the unimaginably far future, be absolute. Let us talk about something that brings the darkness of space into direct contact with human experience in a way that statistics and distances cannot. About the specific visual experience of deep sky observation and what it reveals about the structure of the darkness we are embedded in. When you look at a dark sky with the naked eye, you are not seeing the universe. You are seeing a tiny, biased, highly filtered sample of it. Your eyes are sensitive to a narrow range of the electromagnetic spectrum, roughly 380 to 700 nanometers, which cosmologists call the optical window. The universe emits radiation at wavelengths ranging from radio waves thousands of meters long to gamma rays with wavelengths smaller than an atomic nucleus. Your eyes detect a sliver. Within that sliver, your eyes detect only sources bright enough to exceed their detection threshold, currently down to magnitude 6 or 7 under ideal conditions, representing stars with specific minimum luminosities at specific maximum distances. Every star you see with the naked eye is within our galaxy. The nearest galaxies, the Magellanic Clouds in the southern sky, are barely detectable as faint smudges. Andromeda is visible to careful eyes as a faint smear in a dark sky, but represents the absolute limit of naked eye extragalactic observation. The vast majority of the universe, in terms of both volume and the count of light-emitting objects, is completely invisible to the naked eye under any conditions. Now consider what a telescope reveals. A small telescope with a 10-centimeter aperture can detect stars down to approximately magnitude 13, increasing the number of visible stars from thousands to millions. It can reveal hundreds of galaxies in the nearest clusters. It can show the disks of the planets, the moons of Jupiter, the rings of Saturn, the surface features of the Moon in extraordinary detail. A larger telescope, a meter-class instrument, can detect stars to magnitude 18 or 19 and reveal thousands of galaxies in a single field of view. The Virgo cluster of galaxies, which appears as a blank region of sky to the naked eye and contains smudges invisible without optical aid, becomes a landscape of interacting and clustering galaxies, each one itself containing billions of stars. The Hubble Space Telescope, positioned above the atmosphere and therefore free of atmospheric turbulence and airglow, can detect objects to approximately magnitude 31. In the famous Hubble Deep Field observations, it pointed at a patch of sky in the constellation Ursa Major, a patch about 1/30th the angular diameter of the full moon, selected because it appeared completely blank in ground-based images and exposed for approximately 10 days. The resulting image showed approximately 3,000 galaxies in that single blank patch of sky. 3,000 galaxies, each containing billions of stars. In a patch of sky you could cover with the tip of your finger held at arm's length. And the Hubble Deep Field represents not a uniquely galaxy-rich region, but a typical patch of sky. Extrapolated to the full sky, this implies approximately 200 billion galaxies in the observable universe. a number recently revised upward to somewhere between 1 and 2 trillion when accounting for galaxies too faint and too distant for even Hubble to detect. 1 to 2 trillion galaxies, each containing on average hundreds of billions of stars. The math produces numbers so large they are essentially meaningless as quantities. They can only be understood as indicating that whatever you can see, the actual universe contains incomprehensibly more. And yet, and this is the crucial point that the Hubble Deep Field illustrates, even in those 3,000 galaxies packed into a fingertip patch of sky, even in that image containing more light-emitting objects than have ever been counted in any comparable area, the dominant visual impression is darkness. The galaxies are small, they are faint, they are points and smudges in a field of black. The black between them is not background, it is the actual content in volumetric terms of the image. The light sources are exceptional features in an ocean of darkness. Let us now talk about the specific number that captures what the universe actually is in physical terms, about the average density of matter in the universe and what it means. The average density of ordinary matter in the observable universe is approximately 4.5 times 10 to the minus 28 kilograms per cubic meter. To understand what this number means in human terms, let us convert it. A hydrogen atom has a mass of approximately 1.67 times 10 to the minus 27 kilograms. The average density of ordinary matter in the universe therefore corresponds to approximately 1 hydrogen atom per 3.7 cubic meters of space. That is, roughly speaking, 1 atom per cubic volume the size of a large filing cabinet. For comparison, the air you are breathing right now contains approximately 2.7 times 10 to the 25th power molecules per cubic meter. Molecules being slightly larger than atoms, containing 2 atoms each for nitrogen and oxygen, which constitute most of air. This is 27 trillion molecules per cubic meter. The ratio between the density of air and the average density of the universe is approximately 10 to the power of 53, 1 followed by 53 zeros. The air around you is 10 to the power of 53 times denser than the average matter density of the universe. This ratio is almost literally incomprehensible. Let us try to approach it from another direction. Take the total mass of the Earth, approximately 6 times 10 to the 24th power kilograms. Spread that mass uniformly throughout a volume with the density of the average universe. How large a volume would it fill? The Earth's mass distributed at the average cosmic density of matter would fill a sphere approximately 62,000 light-years in radius, roughly the diameter of the Milky Way galaxy. All the matter that makes up the Earth, spread out to the density that is average for the universe, would fill a volume the size of our entire galaxy. Everything on Earth, every mountain, every ocean, every atom in every living creature, every piece of metal ever mined, every molecule of air, all of it, spread to average cosmic density, would barely fill the Milky Way. And the Milky Way is a dense object by cosmic standards. Our galaxy has significantly above average matter density. Galaxies are the concentrations, the peaks, the dense accumulations that arise from gravitational collapse. The average of the universe is pulled down by the vast voids between and around them. The universe is not mostly matter. Matter is a trace contaminant in an ocean of space. Let us now talk about what the darkness means from the perspective of information, about what the finite speed of light and the vast distances of space imply for how much we can actually know about the universe. Every observation in astronomy is an observation of the past. Light travels at approximately 300,000 kilometers per second, fast by any human standard, but finite. The light reaching your eyes from the sun left the sun 8 minutes and 20 seconds ago. The light reaching your eyes from the moon left the moon about 1.3 seconds ago. The light reaching your eyes from the nearest star, Proxima Centauri, left that star 4.24 years ago. When you look at the Andromeda galaxy, the nearest large galaxy at 2.537 million light-years, the light reaching you left Andromeda 2.537 million years ago. At that time, Homo sapiens did not exist. Homo habilis was just beginning to develop stone tools on the African savanna. Whatever Andromeda looks like today, whatever stars have been born, whatever stars have exploded, however the galaxy has evolved in the intervening 2.537 million years, we will not know for another 2.537 million years, when the light from those events finally arrives. The Virgo cluster at 65 million light-years shows us its state from 65 million years ago, before the mass extinction that ended the Cretaceous, before the asteroid that killed the non-avian dinosaurs, before the current configuration of continents, before the Alps were fully formed. Whatever is happening in the Virgo cluster today, we will not learn of it for 65 million years. The most distant galaxies observable by Hubble and James Webb are being seen as they existed when the universe was less than 1 billion years old, less than 7% of its current age. We are observing those galaxies in a state they left behind more than 12 billion years ago. The galaxies themselves have evolved enormously since then. The specific galaxies we see in Hubble Deep Field images may have long since merged with neighbours, changed their morphology, altered their star formation rates. What those galaxies look like today, we do not know and cannot know. The observable universe is therefore not a snapshot of what currently exists. It is a time-layered archive of light that has been travelling toward us for varying amounts of time. 8 minutes for the Sun, 4 years for the nearest star, millions of years for nearby galaxies, billions of years for the most distant observable objects. Every point of light in the night sky represents a different historical moment, a different depth into the past. The universe as we observe it is not a single moment, but a superposition of moments, spanning 13.8 billion years of cosmic history. We see the nearest stars as they are almost now. We see distant galaxies as they were billions of years ago. And the cosmic microwave background, the most distant light we can observe, shows us the universe as it was 380,000 years after the Big Bang, the earliest state from which any photons have survived to reach us. Beyond that, before recombination, is darkness in a specific sense. Not the darkness of empty space, but the darkness of causal inaccessibility. Light from before recombination cannot reach us, because the universe was opaque. Photons scattered constantly and could not travel freely. Whatever happened in the first 380,000 years of the universe's existence cannot be directly observed through electromagnetic radiation. We can infer it, we can model it, we can look for its signatures in the patterns of the cosmic microwave background and in the large-scale structure of the universe today, but we cannot see it directly. The darkness of the early universe is not the darkness of absence, but of opacity, a different kind of barrier between us and the earliest moments of cosmic history. Let us now talk about something that sits at the intersection of the darkness of space and the deepest questions of physics, about quantum vacuum and the nature of what appears to be empty space at the smallest scales. Ordinary empty space, the interstellar void, the intergalactic medium, the apparent nothingness between atoms and between galaxies, is not actually empty at the quantum mechanical level. Quantum field theory, the framework underlying our most precise understanding of particle physics, describes the vacuum not as absence, but as a fluctuating sea of quantum fields, whose lowest energy states are not zero. This means that empty space has energy. Not energy in any form we can extract or use. It is the zero-point energy of the quantum fields, the irreducible minimum energy that the fields carry even in their lowest possible state. But energy nonetheless, with real physical consequences. One consequence is the Casimir effect, a measurable attractive force between two uncharged conducting plates, placed very close together in what appears to be empty space. The force arises because the quantum vacuum fluctuations between the plates are constrained by the geometry. Only wavelengths shorter than the plate separation can fit in the gap, while the fluctuations outside the plates are unconstrained. This asymmetry creates a pressure difference, pushing the plates together. The Casimir effect has been measured in laboratory experiments and matches theoretical predictions with remarkable precision. Another consequence is Hawking radiation, the theoretical prediction by Stephen Hawking that black holes are not perfectly black, but slowly emit thermal radiation due to quantum effects near the event horizon. The mechanism involves pairs of virtual particles, quantum fluctuations of particle-antiparticle pairs, appearing near the horizon, with one particle falling in and the other escaping as real radiation. Over astronomically long timescales, this process causes black holes to slowly lose mass and eventually evaporate entirely. The quantum vacuum is therefore not nothing, it is something, a specific physical state of the quantum fields, with specific energy content and specific physical effects. The darkness of space is pervaded by this quantum activity, invisible to any macroscopic measurement, but fundamentally shaping the physics of what empty space actually is. This creates one of the deepest unsolved problems in all of physics, the cosmological constant problem. The dark energy driving the accelerating expansion of the universe has an energy density that has been measured. Calculations from quantum field theory predict what the energy density of the quantum vacuum should be. The two numbers differ by approximately 120 orders of magnitude, a factor of 10 to the 120 power. This is the largest known discrepancy between a theoretical prediction and an experimental measurement in the history of physics. We do not understand why space has the energy density it has. We do not understand the relationship between quantum vacuum energy and dark energy. The darkness of space, the apparent nothingness of the void, sits at the intersection of quantum mechanics and general relativity in a way we cannot yet reconcile. The emptiness is not just dark but theoretically problematic, a standing reminder that our deepest understanding of physics is incomplete. Let us now talk about something that takes the discussion of cosmic darkness from the very large to the very small, about the darkness within ordinary matter itself and what it reveals about the nature of the solid objects we interact with every day. Matter, the stuff that makes up stars, planets, rocks, chairs, your body, is not solid in the sense that everyday experience suggests. At the atomic level, matter is almost entirely empty space. A hydrogen atom, the simplest atom, consisting of a proton and a single electron, is a useful starting point. The proton at the center has a radius of approximately 0.85 femtometers, 0.85 times 10 to the minus 15 meters. The electron orbits at a distance described by the Bohr radius, approximately 53 picometers, 53 times 10 to the minus 12 meters. The ratio between the orbit radius and the proton radius is approximately 62,000. If you scaled the proton to the size of a golf ball, about 4 centimeters, the electron's orbit would have a radius of approximately 2.5 kilometers. The atom would be 5 kilometers in diameter, with a golf ball at the center and a speck the size of a small mote of dust orbiting 2.5 kilometers away. Between the golf ball and the mote of dust, nothing. Vacuum. No matter, no particles. Just the quantum fields that define the probability distribution of where the electron might be found if measured. This is the structure of all ordinary matter. Every atom is mostly empty space. A tiny, dense nucleus surrounded by electron orbitals that are themselves extremely small and separated from the nucleus by enormous relative distances. The solid surfaces you touch, the floor beneath you, the chair you might be sitting in, the body you inhabit, appear solid because of electromagnetic forces between electron clouds, not because of any actual physical density. The electrons of one atom repel the electrons of another through electromagnetic interaction, creating the experience of solidity and impenetrability. But if you could somehow neutralize those electromagnetic forces, ordinary matter would interpenetrate freely. The atoms would simply pass through each other, the empty space of one object merging with the empty space of another. Neutron stars, the collapsed remnants of massive stars after supernova explosions, provide a reference point for what matter looks like when the empty space is removed. In a neutron star, the density is so extreme that the normal atomic structure collapses entirely. Electrons are forced to merge with protons, producing neutrons, and the resulting matter is packed to nuclear density, approximately 4 times 10 to the 17th power kilograms per cubic meter, compared to the density of water at 1,000 kilograms per cubic meter. A neutron star, the size of a mountain on Earth, the size of a city in 2 dimensions, would have a mass greater than the Sun. The empty space within normal matter has been removed, leaving only the nuclear material. The darkness within matter mirrors the darkness of the larger cosmos. At every scale from subatomic to cosmological, the universe is defined by the exceptional nature of its dense concentrations, nuclei, atoms, stars, galaxies, embedded in vast regions of near nothingness. Let us now talk about what the darkness of space means for the philosophical question of uniqueness, about what the emptiness implies regarding our own place in the universe. Carl Sagan famously noted that the Earth is a pale blue dot, a mote of dust suspended in a sunbeam. But the mathematical reality of our position is even more extreme than that phrase captures. The Earth is not merely small. It is located in a region of the universe that is, by cosmic standards, almost certainly exceptionally dense and complex. The universe, on average, contains 1 atom per cubic meter of space. Your body contains approximately 7 times 10 to the 27th power atoms, 7 billion billion atoms, in a volume of roughly 0.07 cubic meters. The density of atoms in your body is approximately 10 to the 28th power times the average density of the universe. You are a concentration of matter 10 billion times more dense than the universe considers typical. The same is true of every object you have ever encountered. The chair you sit in, the building you inhabit, the city outside, the planet beneath you. Every human artifact, every geological formation, every body of water, every atmosphere, all of it exists at densities orders of magnitude above the cosmic average, in a region of the universe, near a star, on a planet, that is extraordinarily unusual by the standards of what most of the universe's volume actually looks like. Most of the universe's volume looks like intergalactic space. Cold, dark, almost devoid of matter, pervaded only by radiation and quantum vacuum fluctuations. The stuff of human experience, matter, heat, light, chemistry, biology, is clustered into a tiny fraction of the universe's volume, in the exceptional concentrations we call stars and planets. The darkness of space is not the background condition that life struggles against. The darkness of space is the dominant condition of the universe. Life, and the matter that supports it, is the exceptional local fluctuation. Let us now talk about something that rarely gets discussed in the context of cosmic darkness, but that illuminates it from an unexpected angle, about bioluminescence and the evolution of eyes, and what the existence of sight in biology tells us about the relationship between life and light. The evolution of eyes, of light-sensing organs, has occurred independently dozens of times in the history of life on Earth. Eyes have evolved independently in vertebrates, in mollusks, in arthropods, in worms, in cnidarians, and in other groups. The camera eye, with its lens, retina, and variable aperture, has evolved independently at least twice, in vertebrates and in cephalopods like octopus and squid, to near identical functional solutions. This convergent evolution of sight is taken as evidence that light sensing provides such significant adaptive advantages that it evolves whenever the environmental conditions make it possible. The environmental condition that makes it possible is the availability of light. Specifically, the electromagnetic radiation in the optical window emitted by the sun and reflected by the Earth's surface and atmosphere. Life on Earth evolved in the light of a particular star, a G-type main sequence star of a specific luminosity and a specific spectral distribution. The optical window of the electromagnetic spectrum, the wavelengths our eyes detect, corresponds almost exactly to the peak emission wavelength of the sun and to the wavelengths at which Earth's atmosphere is most transparent. This is not a coincidence. Eyes evolved to detect the light that is available. In the darkness of deep space, far from any star, eyes would be useless. The cosmic microwave background at 2.7 Kelvin emits in the microwave region, far below the optical window. Interstellar hydrogen emits in the radio spectrum. Without a nearby star, the optical spectrum is essentially empty. There is nothing to see in the wavelengths that vision has evolved to detect. Life as we know it requires not just matter, but light. Not just any light, but light of a specific spectral character. Not just that spectral character anywhere, but delivered at a specific intensity, enough to power photosynthesis and illuminate surfaces for vision, not so intense as to damage biological molecules. The narrow range of conditions that make eyes useful, that make photosynthesis possible, that make the visual experience of a sunlit landscape conceivable, these conditions exist only in the immediate vicinity of a star, in the thin habitable zone where stellar light reaches a planetary surface at the right intensity. The overwhelming volume of the universe contains none of these conditions. The darkness is not just the absence of visual experience, it is the absence of the conditions that make visual experience biologically possible. Let us now talk about the darkness of space in the context of specific historical observations that changed how humans understood their cosmic situation, about the moments when the darkness became measurable rather than merely apparent. The first serious estimate of the distance to the stars was made by Friedrich Bessel in 1838 through the technique of stellar parallax, measuring the apparent shift in a nearby star's position against the background of more distant stars as the Earth moves around the Sun. Bessel measured the parallax of the star 61 Cygni and found a distance of approximately 10.3 light-years, a number that, in the context of the distances humans had previously contemplated, was almost incomprehensibly large. Before this measurement, the scale of interstellar distances was genuinely unknown. The impossibility of measuring stellar parallax before the 19th century, the instruments were simply not precise enough, meant that there was no empirical basis for any specific estimate. Hypotheses ranged from distances of a few light-years to enormous numbers based on philosophical reasoning. Bessel's measurement provided the first empirical number. The response among educated contemporaries was instructive. Many found the number so large as to be difficult to reconcile with any coherent picture of the universe. If the nearest star is 10 light-years away, and if stars are distributed roughly uniformly through space, the number of stars in the galaxy becomes enormous, far larger than the pre-telescopic imagination had assumed. The darkness between the stars was not a relatively short, empty gap before the next star, but an emptiness of scale so great that crossing it would take human civilization's entire recorded history to traverse at any speed we could achieve. A later landmark was the measurement of the distances to galaxies, objects then called nebulae and debated as to whether they were nearby gas clouds within the Milky Way or distant island universes comparable to the Milky Way itself. In the 1920s, Edwin Hubble used Cepheid variable stars, stars whose pulsation period is directly related to their intrinsic luminosity, to measure the distance to the Andromeda Nebula. His result was approximately 900,000 light-years, far outside the Milky Way, confirming that Andromeda was a separate galaxy. The universe immediately became vastly larger than the Milky Way in the estimation of astronomers, and the darkness between galaxies, the intergalactic void, revealed itself to be a different kind of emptiness from interstellar space, even more extreme in its desolation. Each successive measurement of cosmic distance has expanded the darkness, pushed the known boundary of the universe further out, and revealed more emptiness between the concentrations of matter. The progression from Greek astronomy, through Bessel, through Hubble, through the current understanding of the cosmic web, represents not an increase in the apparent density of the universe, but a progressive revelation of its emptiness. Let us now talk about something that is active scientific research right now, about the most distant objects ever observed, and what the James Webb Space Telescope has revealed about the earliest epochs of cosmic history. The James Webb Space Telescope, launched in December 2021 and achieving full scientific operations in 2022, has pushed the frontier of observational astronomy into regimes previously inaccessible. Its infrared sensitivity and its position in space, at the second Lagrange point, 1.5 million kilometers from Earth, allow it to observe objects at cosmological redshifts that were previously beyond reach. Early results from Webb included the detection of galaxies at redshifts exceeding 10, meaning the universe had expanded by a factor of more than 11 since the light left those galaxies. These galaxies were shining when the universe was less than 500 million years old. Some candidates at even higher redshifts have been identified, potentially corresponding to the universe at ages of 200 to 300 million years, very close to the epoch when the first stars formed. Some of these early galaxies were surprising. Several appeared more massive and more evolved than models of early galaxy formation predicted. Galaxies that seemed to contain billions of solar masses of stars appeared to exist at epochs when our models suggested there had not been enough time to accumulate that much stellar mass. These observations have prompted revisions to models of early galaxy formation and star formation efficiency. The James Webb has also provided the most detailed spectra yet of exoplanet atmospheres, detecting carbon dioxide in the atmosphere of the hot Jupiter WASP 39b, detecting water vapor and other molecules in other exoplanet atmospheres, and beginning the characterization of smaller, potentially more habitable planets. The detection of carbon dioxide, a molecule directly relevant to planetary habitability, in an exoplanet atmosphere for the first time demonstrated the capability that will eventually be turned toward more Earth-like planets. But for the darkness question, the most relevant Webb results are the deep field images of blank patches of sky exposed long enough to reveal the faintest objects. Webb's deep fields reveal the same qualitative result as Hubble's, a field of galaxies in every direction, thousands of them in a patch of sky smaller than the full moon, extending to the earliest observable epochs. But at longer wavelengths, penetrating to higher redshifts, revealing the universe at even earlier times. And in those images, the same visual impression as in the Hubble deep fields. Galaxies, yes, thousands of them, each containing billions of stars. But the dominant visual feature, darkness, black space between the galaxies, black space between the stars within the galaxies. An image whose majority content by area is the absence of light. The most powerful telescope ever built, looking at a region of sky selected for its apparent emptiness, producing images of the earliest observable universe, and the overwhelming impression is darkness, punctuated by light, rather than light punctuated by darkness. Let us now talk about something that sits at the intersection of physics and philosophy, about what the darkness of space means for the nature of time and the universe's relationship to information. The universe began 13.8 billion years ago in a state of extraordinarily high density and temperature from which it has been expanding and cooling ever since. This beginning had specific properties, a very low entropy state, a state of extraordinary order and uniformity on large scales, from which the universe has been evolving toward higher entropy, greater disorder, more even distribution of energy. The darkness of space is related to this arrow of time. Stars shine because they are hotter than the space around them. Energy flows from the high-temperature stellar interior to the cold surrounding space through radiation. The light you see from stars is the universe in the process of equilibrating, hot regions cooling, cold regions warming, entropy increasing. The darkness of space is the low-temperature reservoir into which stellar energy is dissipating. This connection between darkness and thermodynamics has a profound implication. The darkness of space, the 2.7 Kelvin background temperature, the cold vacuum of interstellar and intergalactic space, is what makes life possible. Life requires the ability to reduce its own entropy, to maintain ordered, low-entropy structures, organisms, cells, proteins, which requires the ability to dump entropy into the environment. We eat food, low entropy, and excrete waste, high entropy, using the difference to maintain our ordered structures. The low-entropy food ultimately derives from the sun. The high-entropy waste ultimately radiates into the cold darkness of space. Without the darkness, without the cold, low-temperature sink into which we can dump entropy, life's thermodynamic engine cannot run. The ability to order our local environments, to build and maintain the complex structures of biology, depends on the availability of the cold, dark void as a destination for the disordered energy we must expel. The darkness is not the enemy of life, it is the condition of life's possibility. The stark contrast between the hot sun and the cold, dark space, between the 5,778 Kelvin surface of the sun and the 2.7 Kelvin background, is what provides the thermodynamic gradient that powers biology, chemistry, and every physical process on Earth. Life feeds on the difference between the light and the dark. Let us now talk about something specific and technical that illuminates what we mean when we say space is dark, about the Olbers paradox resolution and what the cosmic microwave background tells us about the actual photon density of space. The cosmic microwave background fills all of space with a nearly uniform distribution of photons at a temperature of 2.7 Kelvin. The energy density of this radiation, the total energy per cubic meter carried by CMB photons, is approximately 4.2 times 10 to the minus 14 joules per cubic meter. This sounds small. It is small. But how does it compare to the energy density of visible starlight in interstellar space? The energy density of starlight in the interstellar medium of the Milky Way, the diffuse background of stellar radiation that permeates the disk of our galaxy, is approximately 10 to the minus 13 joules per cubic meter. Comparable in order of magnitude to the CMB energy density, though the starlight is at optical frequencies rather than microwave frequencies. Outside galaxies, in the intergalactic void, the stellar radiation background drops dramatically. The integrated light from all galaxies, spread over the volume of the universe, gives an optical background energy density of approximately 10 to the minus 18 joules per cubic meter, 10,000 times less than the CMB energy density in intergalactic space. What this means? In intergalactic space, the universe is actually more energetically dominated by the microwave background, the afterglow of the Big Bang, than by all the light from all the stars in all the galaxies that have ever existed. The 380,000-year-old relic radiation of the early universe outweighs the accumulated light of 13.8 billion years of stellar activity in terms of energy density. This is a remarkable statement. The Big Bang still dominates the energetic content of empty space more than its photons produced by stars and galaxies. The darkness of intergalactic space, the absence of visible light, is accompanied by an invisible ocean of microwave radiation that contains more energy per cubic meter than the visible light from all cosmic history. The darkness has energy. It is not energetically inert. It is saturated with the thermal radiation of the early universe, too cool for human eyes to detect, but physically real and cosmologically dominant. Let us now talk about the specific measurements that have been made of the integrated light of all galaxies, the attempt to literally measure how much light the universe produces, averaged over its entire volume, and what these measurements reveal about the darkness. The extragalactic background light, the total accumulated electromagnetic radiation from all stars and galaxies throughout cosmic history, has been measured by several missions and instruments. The task is technically difficult because this background must be separated from the much brighter foregrounds: zodiacal light, sunlight scattered off interplanetary dust, airglow, and diffuse galactic light, starlight scattered off interstellar dust. The New Horizons spacecraft, famous as the probe that flew past Pluto in 2015, has contributed unexpectedly to this measurement. At its current position in the outer solar system, beyond 50 astronomical units from the Sun, the zodiacal light, the dominant source of background light in the inner solar system, has faded to negligible levels. This makes New Horizons an ideal platform for measuring the true extragalactic background light without contamination from the solar system. Measurements from New Horizons and from other instruments suggest that the optical extragalactic background light is approximately 2 to 3 times brighter than what can be accounted for by all galaxies detected in deep surveys like the Hubble Ultra Deep Field. This discrepancy has been actively debated. One proposed explanation is that there are many more faint, diffuse galaxies and intergalactic stars than deep field surveys have detected. Another is systematic errors in the measurements. The question is not fully resolved, but the critical point is this: even taking the higher estimates, even if the true extragalactic background light is several times brighter than galaxy counts suggest, it is still extraordinarily faint. The night sky on Earth is far brighter than the extragalactic background light, even on the clearest nights, because of airglow and zodiacal light. If you removed the Earth's atmosphere and moved to the outer solar system, the sky would still be almost completely dark, the sum total of all the light from all the galaxies in the observable universe, spread over the full sky, would be faint enough that you would notice it, only because there would be no airglow drowning it out. The total light output of the observable universe, averaged over the full sky, is roughly equivalent to 60 times the brightness of the faintest stars visible to the naked eye. Not 60 bright stars, the equivalent of 60 stars at the threshold of naked eye detection, spread over the entire sky. This is how dark the integrated light of the universe is when spread over the full celestial sphere. 1 trillion galaxies, each containing hundreds of billions of stars. Their combined light, summed over 13.8 billion years, is barely enough to provide a faint background glow. The darkness wins overwhelmingly. Let us now talk about what black holes reveal about the darkness, about the most extreme form of absence in the physical universe, and what it means that light itself cannot escape from them. Black holes are regions of space-time where the gravitational field is so strong that the escape velocity exceeds the speed of light. They form when matter is compressed beyond the Schwarzschild radius, the critical radius below which an object's gravitational field becomes strong enough to prevent light escape. For the Sun, this radius is about 3 kilometers. If you could compress the entire Sun into a sphere 3 kilometers in radius, it would become a black hole. For the Earth, the Schwarzschild radius is about 9 millimeters. Once matter crosses the event horizon, the boundary of a black hole, it cannot return to the external universe. No information can escape. Not light, not radio waves, not any form of electromagnetic radiation. The interior of a black hole is causally disconnected from the rest of the universe. Whatever happens inside the event horizon cannot influence anything outside it. This makes black holes the darkest objects in the universe in the most fundamental physical sense. Not dark because they fail to emit light, they are dark because the geometry of space-time makes light emission impossible. The darkness is built into the causal structure of space itself. Supermassive black holes, the monsters at the centers of most large galaxies, range from millions to tens of billions of solar masses. The one at the center of the Milky Way, Sagittarius A star, has a mass of approximately 4 million solar masses and an event horizon radius of about 12 million kilometers, roughly 17 times the radius of the Sun. The one at the center of the galaxy M87, the first black hole to be directly imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses and an event horizon radius larger than our entire solar system out to Pluto. Black holes have been imaged not by detecting their event horizons directly, which emit no light, but by detecting the hot gas and plasma that fall toward them, heated by compression and friction to temperatures of billions of degrees and emitting intensely across the electromagnetic spectrum. The black hole itself appears as a dark shadow against this bright background, the most literal possible visualization of darkness surrounded by light. The image of M87 star released in 2019, the orange ring of hot plasma with a dark center, is the most direct human visualization of a physical region from which no light can escape. The darkness at the center of that image is not the darkness of empty space between sources. It is the darkness of a location where the laws of physics prevent any photon from escaping the gravitational grip of concentrated mass. It is darkness in the most absolute physical sense conceivable. And black holes are not rare. Every large galaxy contains a supermassive black hole at its center. Stellar mass black holes, formed in the deaths of massive stars, are estimated to number somewhere between 100 million and 1 billion in the Milky Way alone. The universe contains more black holes than there are stars visible to the naked eye from anywhere in the galaxy. The darkness has structure, it has geometry, it has mass. The darkness is not nothing. Some of it is the most extreme concentrations of matter that physics allows, disguised as absence. Let us now talk about what all of this means for the question of how unusual our experience is, about the relationship between the darkness that constitutes most of the universe and the narrow conditions that allow the experience of anything at all. The experience of experience, consciousness, awareness, the capacity to ask questions about the universe, requires a physical substrate. That substrate, as far as we know, requires certain specific conditions. Matter in sufficient complexity to sustain the organizational structures of biology. Energy flows to power the thermodynamic processes that maintain biological order. Temperature ranges compatible with liquid water chemistry. The presence of heavy elements forged in stellar interiors. An environment stable enough for the slow work of evolution to accumulate complexity over billions of years. All of these requirements point toward the same thing: proximity to a star, on a rocky planet, in a galaxy with sufficient heavy element enrichment, at a cosmic epoch late enough for multiple generations of stellar evolution to have produced those heavy elements, but early enough that sufficient fuel for stellar activity remains. The universe has been in the right epoch for these conditions for approximately the last 10 billion years, after the first generation of stars had time to enrich the interstellar medium with heavy elements, and will remain in a roughly comparable epoch for perhaps another 100 trillion years, as red dwarfs continue to burn their fuel on extraordinarily long timescales. But the conditions are not uniformly distributed through space. They require being in a galaxy with sufficient metallicity, on a planet in a circumstellar habitable zone, on a planet with the right chemistry, the right geological activity, the right atmospheric composition, the right magnetic shielding, the right stability of orbit. The fraction of the universe's volume that satisfies all these conditions simultaneously is extraordinarily small. The relevant volume is essentially limited to planetary surfaces around certain types of stars in certain regions of certain galaxies. This volume, compared to the volume of intergalactic voids or even interstellar space, is negligible by any measure. The experience of light, of warmth, of complexity, of awareness, all of this happens in an infinitesimally small fraction of the universe's volume. The vast majority of the universe is dark and cold and simple, governed by nothing more complex than the slow drift of hydrogen atoms in a cooling void. We are the exception, the concentrated, improbable, extraordinarily unlikely exception. Everything you have ever seen or felt or known exists in a tiny bubble of atypical conditions, surrounded by an overwhelming universe that knows nothing of any of it. The darkness is the truth of the universe. The light is the accident. Let us talk about something that connects the darkness of space to the most intimate aspects of human experience, about the specific effect that genuine darkness has on the human nervous system, and why our biology evolved in a way that makes the true darkness of space not just intellectually, but physically alien to us. Human eyes adapted over millions of years of evolution on the surface of a planet with a day-night cycle governed by a nearby star. The retina contains two types of photoreceptors: cones, concentrated in the central fovea, responsible for color vision and detail resolution in bright conditions, and rods, distributed across the peripheral retina, far more sensitive to light and responsible for vision in dim conditions. The rods are approximately 1,000 times more sensitive to light than the cones, capable of detecting single photons under ideal conditions. Dark adaptation, the process by which the eyes adjust to low light conditions, takes approximately 20 to 30 minutes to complete. During this time, the pupil dilates to its maximum diameter of about 8 millimeters. The visual processing system shifts from cone-dominated to rod-dominated, and the concentration of rhodopsin in the rods, the photosensitive pigment that triggers visual signals, increases to its maximum. After full dark adaptation, the eye is operating at close to its physical limit of sensitivity. Even at this peak sensitivity, fully dark-adapted human eyes require a minimum illuminance of approximately 10 to the power of -9 candela per square meter, roughly the illuminance of the darkest accessible sky on Earth under ideal conditions. Below this threshold, vision fails. The eye is at its physical sensitivity limit and cannot do better. Now consider interstellar space. The illuminance in the middle of interstellar space, far from any star, receiving only the diffuse background of accumulated starlight, is orders of magnitude below the threshold of even the most dark-adapted human eye. In the depths of interstellar space, fully adapted human eyes would detect nothing, absolute visual blackness. But the brain does not accept absolute blackness passively. Research on sensory deprivation, on humans placed in conditions of complete absence of visual stimulation, shows that the visual cortex, deprived of input, does not go quiet. It generates its own. Phosphenes, the lights you see when you press on your closed eyes, appear. Visual hallucinations of geometric patterns, then more complex shapes, then fully formed imagery emerge after extended periods of complete darkness. The brain interprets the absence of visual information as information itself and begins filling in the void with self-generated content. This means that humans placed in the true darkness of interstellar space, even setting aside the obviously lethal physical conditions, would not experience emptiness. They would experience their own visual cortex producing images in the absence of external input. The darkness would be internally populated by the artifacts of neural activity. The brain does not have a representation for true nothingness. It has never needed one. For the entire evolutionary history of the visual system, darkness always contained something. Stars at night, ambient light filtered through eyelids during sleep. the faint bioluminescence of the deep ocean. Absolute darkness, the darkness of true interstellar space, is outside the range of conditions the brain's visual system was built to handle. In this specific sense, the darkness of space is not just spatially alien, but cognitively alien. We cannot directly experience it, even with our most sensitive biological instruments. It exceeds the range of what our nervous systems evolved to process. Let us now talk about something that takes the darkness from the cosmic scale back to the scale of the human body, about the darkness inside matter itself, and about what the quantum mechanical description of atomic structure reveals about the nature of the material world. We touched on this earlier, the vast, empty space within atoms. Let us go deeper. Let us follow the structure of matter down to the limits of what physics currently understands. An atom consists of a nucleus, protons and neutrons packed into a volume roughly 10 to the minus 15 meters in diameter, surrounded by electrons in quantum mechanical orbitals at distances roughly 10 to the minus 10 meters from the nucleus. The ratio of the atom's size to the nucleus's size is approximately 100,000. The atom is mostly empty space. But what about the nucleus itself? Is it dense? In the sense that matters for everyday experience, yes. Nuclear matter at approximately 2.3 times 10 to the 17th power kilograms per cubic meter is the densest state of ordinary matter outside of black holes. But even here, quantum mechanics introduces a subtlety. Protons and neutrons, the constituents of nuclei, are not fundamental particles. They are composite objects made of quarks. A proton contains 3 quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force mediated by gluons. The quarks themselves are point particles at the current limits of experimental resolution. They have no measurable size. The gluons that hold them together fill the interior of the proton with a complex quantum field, but the quarks themselves are essentially mathematical points with no spatial extent. What this means, the matter that makes up ordinary objects, the quarks in the nuclei of atoms, consists of point particles separated by quantum fields. There is no underlying solid substrate. There is no surface of ultimate density below which you cannot go. The apparent solidity of matter, the resistance that makes a table feel solid, that makes a floor bear your weight, is an emergent property of quantum mechanical forces between clouds of probability distributions of essentially point-like particles. The darkness inside matter is therefore not the darkness of empty space between substantial objects. It is the darkness of a quantum field, a description of the probability of finding a particle if you look, with no underlying classical reality beneath it. When you push down on a table and feel resistance, what you are feeling is not matter touching matter, but electromagnetic repulsion between electron clouds, probability distributions pushing against probability distributions, with no actual contact between any solid surfaces, because no solid surfaces exist at the quantum level. The universe is not made of stuff, it is made of fields. And the fields, outside of the regions where particles are most likely to be found, are empty in a sense that is genuinely dark. Not the darkness of interstellar space, which is at least described by classical physics, but the darkness of quantum superposition, the darkness of unobserved probability. Let us now talk about something that sits at the outer edge of current physics, about the multiverse hypothesis, and what it implies about the nature of the darkness we cannot observe. Several independent lines of reasoning in modern physics converge on the suggestion that the observable universe, the 93 billion light-year diameter sphere from which light has had time to reach us, may be only a tiny portion of a much larger structure that is itself embedded in something larger still. The first line is inflationary cosmology. The leading theoretical framework for explaining certain features of the early universe, the remarkable uniformity of the cosmic microwave background, the flatness of the universe's spatial geometry, the absence of predicted relics from early universe phase transitions, invokes a period of extraordinarily rapid exponential expansion called inflation that occurred in the first fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 to the 26th power, and possibly enormously more, in an incredibly short time. Many models of inflation predict eternal inflation, the idea that inflation, once started, continues somewhere forever. In this framework, inflation only stops in certain regions where local conditions cause the inflationary process to end. These regions become what we would call bubble universes, each potentially with different physical constants and properties. The inflating space between and around the bubbles continues to inflate, producing more bubbles in a process that never globally ends. If eternal inflation is correct, the observable universe, everything within our cosmic horizon, is one bubble in an endlessly inflating sea. The darkness beyond our horizon is not empty, but filled with inflationary space and other bubble universes, permanently inaccessible to us because the space between us and them is expanding faster than any signal can cross. The second line is string theory's landscape. String theory, the leading candidate for a quantum theory of gravity, predicts an enormous number of possible solutions, each corresponding to different values of the fundamental constants, different numbers of spatial dimensions, different particle physics. The number of possible solutions is often estimated as 10 to the power of 500. Each solution would correspond to a different possible universe with different physical properties. If the landscape is real, the question becomes not what are the unique fundamental constants of physics, but why we observe the particular values we do. The anthropic answer, that we observe values compatible with our existence because we could not exist to observe incompatible values, becomes relevant in a multiverse where all values are realized somewhere. Neither eternal inflation nor the string landscape is directly testable with current technology. They remain hypotheses, motivated by theoretical considerations and indirect evidence, but not confirmed by direct observation. The darkness beyond our horizon prevents any direct access to whatever lies beyond it. But they illustrate the extreme version of the darkness proposition. Not just darkness in the sense of distant galaxies we cannot currently resolve. Not just darkness in the sense of the cosmic microwave background, showing us the last scattering surface but nothing before it. But darkness in the sense of potentially infinite regions of spacetime, perhaps containing other universes with different laws of physics that are permanently, fundamentally, not just currently, inaccessible to any observation from within our bubble. The darkness may not just exceed our observational capabilities. It may be an inherent feature of the geometry of existence, a permanent feature of what it means to be in one bubble among many. Let us now talk about something concrete and near, about the specific experience of the International Space Station astronauts and what they report about the visual character of space from orbit. The International Space Station orbits at an altitude of approximately 400 kilometers, close enough to Earth that the planet dominates the visual field when looking down. From orbit, Earth is an extraordinary sight. The curvature of the horizon visible, the thin blue line of the atmosphere visible as a fragile, luminous layer against the blackness of space above. The surface below covered in clouds and geography and the faint glow of cities at night. But the astronauts who have described looking the other direction, away from Earth and into space, describe something specifically striking about the quality of the darkness. Stars in orbit are visible continuously. The sun sets and rises approximately every 45 minutes as the station circles the Earth. And in the brief dark periods, the stars appear not as they do from Earth, but with different quality. The stars do not twinkle. Atmospheric turbulence, the varying density of air that refracts starlight differently from moment to moment, produces the twinkling effect seen from Earth's surface. In orbit above virtually all of the atmosphere, the stars are steady points of light, sharper, more precise. Less romantic in some ways, the twinkling that makes stars seem alive from Earth is absent, but more honest. Stars as they actually are, point sources of light at vast distances, separated by darkness. The darkness between the stars, astronauts report, is more absolute than any darkness they have encountered on Earth. On Earth, even in the darkest desert or the deepest cave, there is some light, reflected from the Milky Way, from air glow, from their own adapted eyes' neural activity. In orbit, in the station's shadow, looking away from Earth, the darkness between the visible stars is specifically, distinctly darker. The absence of atmosphere means there is no scattering of light between sources. The darkness between stars is not a gradient fading into starlight, but a sharp contrast. Light and dark, sources and void. Russian cosmonauts who spent extended periods on the Mir space station in the 1980s and 1990s, before the ISS, in a smaller, simpler craft, reported that the extended experience of looking at space produced a specific psychological effect. Not fear exactly, though fear was sometimes present. Something more like awe, crossed with a specific kind of loneliness. The recognition that the environment outside the walls of the spacecraft was absolutely inhospitable in a way that no environment on Earth is. That there was no gradient between the safety inside and the danger outside. That a centimetre of metal was the entire boundary between life and a death that the universe regarded with complete indifference. This reaction, documented in the psychological records of long-duration spaceflight, is sometimes called the overview effect. The term was coined by Frank White to describe the cognitive shift reported by astronauts who see Earth from space. A recognition of the planet's fragility, its isolation, its beauty in the context of the surrounding darkness. But the other side of the overview effect, the experience of the darkness itself rather than of Earth within it, is less discussed and perhaps more profound. The darkness does not care about you. This sounds obvious when stated directly. Of course, the universe is indifferent. Everyone knows the universe is indifferent. But there is a difference between knowing it abstractly and experiencing it from within a small pressurized container flying through vacuum at 7.7 kilometers per second. The astronauts who have been there report that the knowing and the experiencing are different things. Let us now talk about something that illuminates the darkness from the perspective of how we measure it, about the concept of astronomical magnitude and why the scale astronomers use to measure brightness is one of the most counterintuitive rating systems in science. The apparent magnitude scale used in astronomy was formalized by the Greek astronomer Hipparchus around 127 BC. He divided the visible stars into 6 magnitude classes: first magnitude for the brightest, 6th magnitude for the faintest visible to the naked eye. The scale was later formalized mathematically by Norman Pogson in 1856, with the definition that a difference of 5 magnitudes corresponds exactly to a factor of 100 in brightness. This means a difference of 1 magnitude corresponds to a factor of approximately 2.512, the 5th root of 100. The scale runs counterintuitively. Lower numbers are brighter. Sirius, the brightest star in the night sky, has an apparent magnitude of -1.46. Venus, at its brightest, reaches approximately -4.9. The full moon is approximately -12.7. The sun is approximately -26.7. Going the other direction, the faintest stars visible to the naked eye are around magnitude 6 to 7. A small telescope reveals stars to magnitude 11 or 12. The Hubble Space Telescope can detect objects to magnitude 31 or 32. The difference between magnitude minus 26.7, Sun, and magnitude 32, Hubble's limit, is approximately 58.7 magnitudes. Each 5 magnitude difference is a factor of 100 in brightness. 58.7 magnitudes corresponds to approximately 10 to the power of 58.7 over 2.5, roughly 10 to the power of 23.5, a factor of about 300 sextillion in brightness. The faintest objects Hubble can detect are approximately 300 sextillion times fainter than the Sun. And yet those objects, the faint smudges in the Hubble ultra-deep field, are themselves entire galaxies containing billions of stars, each comparable to the Sun. They are faint because of distance. The combined light of hundreds of billions of suns at distances of billions of light years is reduced to that faint signal. Now go further. Between those faint galaxy smudges in the Hubble deep field, in the dark pixels between the galaxy images, how bright is the sky? The background brightness between resolved sources in the Hubble ultra-deep field corresponds to a surface brightness of approximately magnitude 29 to 30 per square arc-second, meaning that the empty appearing dark space between the visible galaxies is itself faintly luminous, lit by the accumulated light of galaxies too faint and too numerous to resolve individually. And this residual glow, this faint illumination of the deep sky between resolved galaxies, is itself being used to search for the signatures of population 3 stars, intergalactic stars stripped from their parent galaxies, and potentially the epoch of reionization. The darkness itself is being mined for information. The darkness contains structure. Even the blackest parts of the deepest images are not perfectly dark. They carry the integrated signal of the entire universe beyond the resolved sources, compressed into a glow below the individual galaxy detection threshold. Let us now talk about something that takes the concept of cosmic darkness and grounds it in a specific physical measurement that anyone with the right equipment can make. About the measurement of the night sky brightness and what it reveals about light pollution, astronomical access, and humanity's relationship with the darkness above. The International Dark Sky Association was founded in 1988 to address the growing problem of light pollution, the brightening of the night sky due to artificial lighting that scatters off the atmosphere and creates a diffuse glow visible from vast distances. Light pollution is not merely an aesthetic problem for astronomers. It represents a fundamental change in the visual environment of the planet, one that has happened extraordinarily rapidly in historical terms. Before the widespread adoption of artificial lighting, before the 20th century in practical terms, the entire human population lived under skies comparable to what is now accessible only in the most remote wilderness areas. The Milky Way was visible to virtually every human who ever lived. The faint stars, the zodiacal light, the counterglow of the Gegenschein, all of these were part of ordinary human visual experience. Today, approximately 83% of the world's population and more than 99% of the population of the United States and Europe live under light-polluted skies. The Milky Way is not visible to approximately 1/3 of the world's population, and to many in developed nations, it has never been seen at all. The generation of humans currently go outside tonight and look up. Find the darkest patch of sky you can access, away from streetlights, away from windows, away from screens. Let your eyes adapt. Give them 20 minutes. Let the rods in your retinas reach their maximum sensitivity. Let the rhodopsin accumulate. Let the visual processing system shift to its most sensitive mode. And then look at what is actually there. If you are lucky enough to be somewhere genuinely dark, a desert, a mountain, a rural field far from any city, you will see the Milky Way, not as a concept, as a thing. A band of light crossing the sky from horizon to horizon, not uniform but structured, brighter in the direction of the galactic center, darker where dust lanes cross the arms, resolved at the edges into individual stars too numerous to count. What you are seeing is approximately 100,000 light-years of galaxy compressed along your line of sight. Hundreds of billions of stars. Thousands of light-years of interstellar gas and dust. The accumulated light of an entire arm of a spiral galaxy, stacked together until it becomes a visible glow. And the space between those stars, the black between the points of light, is so large that the human mind cannot hold it. The nearest star to the Sun is 4.24 light-years away. Light travels at 299,792 kilometers per second. In the time it takes you to blink, approximately 150 milliseconds, light covers about 45,000 kilometers. At that speed, it would still take 4.24 years to reach the nearest star. And in the space between here and there, in those 40 trillion kilometers of interstellar void, there is, on average, 1 atom per cubic centimeter. 1 atom, per volume the size of your fist. That is what the darkness between stars actually contains. Now look further. If conditions are good and your eyes are fully adapted, you can see the Andromeda galaxy. A faint smear in the constellation Andromeda, visible to the careful eye as a slightly brighter patch of sky. That light left Andromeda 2.537 million years ago. At that moment, Homo sapiens did not exist. The ancestors looking up at African skies were Homo habilis, small-brained, stone tool-making, standing at the very beginning of the long path that eventually produced you standing here tonight looking back. That faint smear contains 1 trillion stars. It is 2.537 million light-years away. And the space between here and there, the 2.537 million light-years of intergalactic void separating us from our nearest large galactic neighbor, is emptier than interstellar space by orders of magnitude. The density of matter in the intergalactic medium is approximately 1 atom per cubic meter. Not per cubic centimeter, per cubic meter. A volume the size of a large piece of furniture contains a single atom. Now think about the rest. 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars, each separated from its neighbors by millions or billions of light-years of intergalactic void at near zero density. The observable universe itself, the 46 billion light-year sphere from which light has had time to reach us, embedded in a larger universe of unknown extent, possibly infinite, filled with matter and energy and structure that we cannot observe because the light from those regions has not yet arrived. And beyond the observable horizon, beyond the reach of any telescope we could ever build, beyond the range of any signal traveling at the speed of light, a darkness that is not the darkness of absence, but the darkness of causal disconnection. Regions of space-time that are not merely far away, but permanently outside our causal future. Things that exist, possibly other galaxies, possibly other forms of matter and energy with different physical laws in different bubble universes, that we can never observe, never detect, never make contact with, regardless of what technology we develop or how long we wait. The night sky is not a window onto the universe. It is a tiny, filtered, biased, time-delayed sample of the nearest fraction of the observable fraction of a possibly infinite cosmos, seen through the narrow optical sensitivity of eyes evolved for an evolutionary purpose that had nothing to do with astronomy. The darkness you see between the stars is the actual content of the universe. The stars are the anomaly, The light is the exception. The darkness is the rule. This should be vertiginous. It should produce a specific feeling that is not quite fear and not quite awe, but something between them. The feeling of having correctly understood the scale of something for the first time. The feeling of a number becoming real rather than merely large. Because there is something important in that vertigo, something that the numbers and the distances and the densities are all pointing toward, something that becomes clear when you hold all of it together at once. You are looking at this. You are here on the surface of a rocky planet orbiting a medium-sized star in an outer spiral arm of one galaxy among 2 trillion, in a universe 13.8 billion years old, having emerged from 4 billion years of biological evolution, with nervous systems sophisticated enough to ask questions about the darkness surrounding you, and sensitive enough to feel something about the answers. The matter that makes up your body was forged in the cores of stars that lived and died before the sun was born. The carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron at the center of your hemoglobin, all of it was produced by stellar nucleosynthesis, scattered into the interstellar medium by supernova explosions, gathered into the molecular cloud that collapsed to form the solar system, incorporated into the rocky body of the Earth, and eventually organized through 4 billion years of chemistry and biology into the structures currently thinking these thoughts. You are the universe's matter having become complicated enough to look at itself and feel something about what it sees. The darkness is the context, the overwhelming, vast, cold, empty, indifferent context in which the improbable concentration of matter and energy and information that constitutes you briefly exists. The darkness does not know about you. It does not care about you. It was here before the Earth formed, and it will be here after the last star has burned out and the last black hole has evaporated and the universe has settled into the maximum entropy equilibrium where nothing interesting ever happens again. But right now, on this particular night, on this particular planet, you are standing in it and looking at it and understanding something about what it is, and that specific thing is not nothing. It might be the most extraordinary thing in the universe, not because it is cosmically significant in any measurable sense. A thinking creature on a small planet in an outer spiral arm does not register on any cosmic scale. You could eliminate the Earth and everything on it, and the universe would continue its expansion undisturbed, its galaxies receding from each other at the same accelerating rate, its dark matter halos maintaining the same gravitational architecture, its temperature dropping the same fraction of a Kelvin per billion years. But something about the darkness becomes different when something is aware of it. Not objectively different, the darkness does not change, but the darkness has produced, through the long, improbable chain of stellar nucleosynthesis and planetary formation and biological evolution and cultural development, something capable of standing at its edge and comprehending its scale. That has never happened anywhere in the 13.8 billion year history of the universe before a certain point in the last few 100,000 years of Earth's history. We don't know if it is happening anywhere else right now. We don't know if the darkness, in its overwhelming majority, has produced any other islands of awareness anywhere in the 2 trillion galaxies within our observable horizon. Maybe it has. Maybe it hasn't. The darkness between us and any possible answer is too vast for us to know. But here, tonight, on this particular patch of the surface of this particular rocky planet, you are standing in the darkness and looking up at it. And that means it is, in this one small, local way, looking at itself. The darkness is not as dark as it was, not because the stars have gotten brighter, not because the voids have filled, but because something in the darkness became aware of the darkness. And awareness is a different kind of light than starlight, one that does not need photons to propagate, one that changes what the darkness means, rather than changing the darkness itself. The universe is old and cold, and almost entirely empty, and utterly indifferent, and astonishingly dark. And yet here we are. looking up at it, understanding it a little, feeling something about it. That may not be cosmically significant, but it is the most significant thing we know of.